So, sequences are essentially functions of an integer variable, and the physical interpretation of the integer variable is the sampling index. I said functions maybe a little carefully, but we need to qualify whether I am talking about real functions or complex functions. Well, I am going to allow complex functions. And again, the natural question is, what is the physical meaning of a complex functions? If I sample a real signal, I am certainly not going to have complex values. So, where would complex signals come from? Well, complex signals for the moment should be thought of as hypothetical extensions of real signals. So, you could think of them as two real signals, one for the real part and one for the imaginary part. And we will use complex signals as a tool to deal with real signals. For the moment, let us think of it with this reassuring note. So, we do not really have complex signals in nature, but we will allow the sequence to be complex, because sometimes it helps us to deal with real signals by bringing in complex signals for a while, doing some work with the complex signals and going back to the real signal, right. Now, in a minute we are going to use a complex signal. So, you see the complex signal comes in as follows. Suppose I were to take a complex number, rotating a complex number which maintains a magnitude of m, starts with an angle of theta naught and rotates at an angular velocity of omega naught. We know how to write this complex number in polar form. The polar form representation of the complex number is very simple. It is m e raised to the power j theta naught plus omega naught t, right. Of course, this is the continuous complex number. Now, let us assume that I were to sample this complex number with a sampling rate of 1. Okay. I would get m e raised to the power j theta naught plus omega naught times n. You see, all the time I am making the convenient assumption that my sampling interval is unity. Let us get used to this assumption. I mean, I am normalizing my time measurement with respect to the sampling interval. Now, you see, the beauty of this representation is that if I were to change its amplitude or its phase, so if I were to change the amplitude or the phase, initial phase theta naught, right. If I were to change the amplitude, m e raised to the power j omega naught n plus phi naught is of course expressible as m1 by m times e raised to the power j omega naught n plus phi naught. On the other hand, this is of course obvious. So, when I change an amplitude to m1, it is equivalent to multiplying that number by m1 by m, simple enough. But the more interesting thing is the phase. So, if I were to change the phase to theta 1, this could be rewritten as m e raised to the power j omega naught n plus phi 0 plus phi 1 minus phi 0. And of course, that can be rewritten as m e raised to the power j omega naught n plus phi naught e raised to the power j phi 1 minus phi naught. So, in either case, you have a multiplying factor here. Whether you take a change of amplitude or a change of phase, it amounts to multiplying the original rotating complex number by a constant, albeit complex. Okay, this is a significant observation. unlike a sinusoid, where when I change the phase, it is not tantamount, it is not the same thing as multiplying the sine wave by a constant. But in a sine wave, of course, when I multiply the amplitude by, when I change the amplitude, is equivalent to multiplication by a constant. So therefore, the beauty of dealing with this rotating complex number is that multiplication by a constant factor, albeit complex, is a correct description of change of amplitude and change of phase, and of course change of amplitude and phase together too. If I change the, and they are independent, if I change the amplitude to m1 and the phase to theta 1 or phi 1, it is equivalent to multiplying by m1 by m e raised to the power j phi 1 minus phi 0. So you can take them together. That means when I now put, it is very clear, if I have a system, instead of dealing with sinusoids now, if I were to deal with these, which we will call phasors. So we call such a rotating complex number a phasor. With a single angular frequency. It is denoted by omega. Now, why are phasors important to us? The real and imaginary parts of phasors are sinusoids with frequency omega, angular frequency omega. Okay, is that clear? That is straightforward, because we can even write down the real imaginary parts. Indeed, if you have a phasor m e raised to the power j omega naught n plus phi naught, this can be decomposed as m cos omega naught n plus phi naught plus m times j sine omega naught n plus phi naught. This is the real part and this is the imaginary part. Each of them is a sinusoid of the same frequency, omega naught. So now I see the connection. I also see the advantage of dealing with phasors. You see, what I am going to do is, I am going to think of a sine wave as the real or the imaginary part of a phasor. And instead of dealing with the sine wave, I am going to think that it was the phasor which was applied to the discrete system, and this would result in a phasor coming out with the same frequency, but a possible change of amplitude and phase, right. And the beauty of dealing with the phasor rather than the sine wave is, this process of changing the amplitude and the phase amounts to multiplying that phasor by a complex constant. So I can represent the action of the system as multiplication by a complex number at that frequency. I want to be able to describe a system like that. Now this requires some thought. Now there is another way of looking at it. The other way is, I can think of a sine, of course I can think of a sine wave as the real or the imaginary part of, but how do I get real or imaginary parts? You see, I must be able to get them with some kind of an operation. So another way to think of it is, when I add two phasors with the same frequency in opposite directions. What I mean by that is, if I were to take two phasors, both of magnitude m, with opposite initial starting angle. So it is like mirror images, the phasors are mirror images of one another. they rotate with a mirror image angular velocity. So, you have omega naught for this one and minus omega naught for the other one. How would I describe this one? This is of course m, and of course both of them are sampled. So, I have m e raised to the power j omega naught n plus theta naught, if you would like, and here I have m e raised to the power minus j omega naught n plus theta naught. You know, they are complex conjugates, these phasors are complex conjugates. If they begin from the opposite starting angle, if they rotate with opposite velocity of the same magnitude, and if they have the same magnitude m, then they are complex conjugates. They always remain as complex conjugates. And on adding them, two times m cos omega naught n plus theta naught. So, in other words, a sinusoid really hides or has in it two oppositely rotating phasors. That is another way to look at it. Now, in many systems that I deal with in discrete time processing, it is sufficient for me to see what the system does to one of these two. They have the same frequency notionally, but with opposite signs. So, one of them has a frequency omega naught, the other one has a frequency minus omega naught. So, in most of the systems, in many, I will not say all systems, we will deal with some exceptions, but in many of the systems that we will deal with, at least when we implement systems in this first course, what would happen is, what that system does to one of these phasors is a mirror image of what it does to the other. So, if I take the phasor rotating in the anti-clockwise, so here I have this, you go back to those two phasors, think of this phasor being applied to the system here, and then think of this phasor being applied to the system. When this phasor is applied to the system, what is going to happen is, out comes a phasor with the same frequency with a changed amplitude and phase. Apply this phasor, same thing, out comes a phasor with the same frequency means minus omega naught here, and a change of amplitude and phase. Now, what is going to happen in most of the systems that we are going to deal with, at least implement, is that the change of amplitude for both of these will be the same. So, both of them will be multiplied by the same m1 by m. But the change of phase here, that means if the starting phase goes from theta 0 to theta 1 here, the starting phase here would go from minus theta 0 to minus theta 1. So, the change of phase would be mirrored. That is what the situation would be in most cases. That means, if I know what happens to one of the phasors, I know what happens to the other. I do not need to analyze what the system does to both individually. And therefore, I can replace my analysis of the sinusoid by an analysis of what happens when I put one of those phasors into the system, because I know what it will do to the other phasor. And once I know what it does to the other phasor, I know what it does to the sine wave. So, what I am saying is, instead of dealing with sine waves, I prefer to deal with phasors. And what is the reason for that? Dealing with phasors means putting a multiplicative constant, multiplying that phasor by a constant. Okay, so what is my requirement? Now, let me put down my requirement of the system, and then I am going to start discussing the properties that will give me that requirement. My requirement from the systems that I design is, when I put in fact, let me do 3 experiments. Experiment 1, I put in a phasor with frequency omega naught and initial phase theta naught. Out comes a phasor A1 e raised to the power j omega naught n naught with plus theta 1, and therefore, the system can be described by just this ratio A1 by A naught times e raised to the power j theta 1 minus theta naught. I can describe the system just by this operation, just by this multiplication at that frequency, isn't it? Experiment 2. Same system, but different input. B naught e raised to the power j omega 1, some different frequency, plus phi 1. Out comes B 1 e raised to the power same frequency, but of course, phase and amplitude can change, and therefore, at omega 1 at that different frequency, this is to be described by the ratio B 1 by B 0 e raised to the power j phi 2 minus phi 1. Experiment number 2. Experiment number 3. Okay, so the same thing, but at frequency. Experiment number 3. Same system. Now put in C0 e raised to the power j omega naught n plus phi 3, let us say, plus C1 e raised to the power j omega 1 n plus phi 4. Out comes D0 e raised to the power j omega naught n plus phi 5, if you like, plus D1 e raised to the power j omega 1 n plus phi 6, and that is not all. D0 by C0 is equal to A1 by A0. D1 by C1 is B1 by B0. First. Secondly, phi 5 minus phi 3 is equal to theta 1 minus theta 0, and phi 6 minus phi 4 is phi 2 minus phi 1. All this must be true. Just to remind you what these quantities are, A1 and A0 were the amplitudes in the first experiment. Theta 1 and theta 0 are the amplitudes in the first experiment. In experiment 2, the amplitudes are phi 2, phi 1, I am sorry, the amplitudes are B0 and B1, and the phases are phi 2 and phi 1. What we are saying is that the way the phase changes and the way the amplitudes change remains the same when I perform the third experiment. So, what are we saying? We are saying something very profound, and this is true for any omega 0, omega 1, any A0, A1, B0, B1, and any theta 0, etc. So, it is a very serious demand I am making of my system. In words, what is my demand? When I put in two complex phasors with different frequencies, what I must get is a sum of two complex phasors of the same two frequencies. The way the amplitudes and the phases change should be the way they change when I give those as individual inputs. So, if I look at what happens to the first phasor and if I look at what happens to the second phasor in their own right without the other being present, I must be able to tell what happens when I put them in combination. Now, this is a very serious demand of the system, and to be able to satisfy this demand, I will need the system to obey many properties. I shall list the properties today, and we shall tomorrow take those properties up one by one. So, for this to happen, right, the system must be linear, shift invariant, stable. These are only terms, these are only names at this point in time. I need to qualify what these mean. So, you see, I mean, just to make a remark here, I am sure that many of us who might have taken a primary course in signals and systems would have heard these terms before. But what is important is to understand why we bring in these terms. It is often that we start talking about system properties without understanding why we should discuss them in the first place. Why we need to discuss them in the first place is now clear. I want to build systems which have that requirement on phasors being obeyed. And if that system must obey those requirements, the only way is when it can be linear, shift invariant and stable. And I need to understand what these three terms mean. We will do that in the next lecture. Thank you.